Welcome back, let's resume. In the previous video, we went through some examples on how to set up hypotheses. That is actually just the first stage of the hypothesis testing problem. Only the first stage. In this video, we talk about the second stage, how to complete the setup or the structure of hypothesis testing. How to complete the problem? Well, that's something we are going to discuss in the next video. We can't do it here, it's too long. Okay, here we go. Here is the structure of the hypothesis, or a little bit more precisely speaking, this is a classification. The null hypothesis is all the same. Mu is about the same as mu naught. That's it. No change, status quo, those kind of things. Now the alternative hypothesis, on the other hand, can be classified kind of like this. Mu is significantly greater than mu naught. In other words, the real mean or the new mean is significantly bigger, or significantly less, or significantly different. The third case is relatively rare. On top of those, we need these two from the population. By the way, the population is associated to the null hypothesis. Mu naught, of course, we know about that. And then on top of that, we need sigma, the population standard deviation. By the way, in the next chapter, in chapter 9, we're going to talk about hypothesis testing problem that is very, very similar to this, except that this one is not given. No population standard deviation. In short, this is actually a stepping stone towards chapter 9. Okay, let's come back to this problem. Enough digression. We need these two from the sample size and the sample mean. And samples usually contribute toward the alternative hypothesis. In the previous type of examples, when we just set up the hypothesis, the sample size didn't play any role whatsoever. The sample mean, well, was helpful a little bit, but still nothing really significant. We need this one. Finally, we need one more thing, so-called the level of significance, which we typically denote as Greek letter alpha. With the hypothesis and then population mean and standard deviation, sample size and sample mean, and also sample standard deviation if necessary. And finally, the level of significance, alpha value, will complete the setup of hypothesis testing problem. But there's a bit of a problem. What exactly does it mean by this alpha? Well, let me try to explain it using the rest of this video. And let me try to do it in two different ways. Number one, graphical way, which is my favorite. And after that, we're going to talk about textbooks method. Here's a visualization of so-called one-tail test, which is basically either this case, mu is significantly bigger or significantly less. By the way, let me copy and paste this one. Okay, oops. Okay. Now let's pay particular attention to left-hand side picture. We have normal picture around population mean mu naught, and this is the null. So we're going to call mu naught as null from this point on. And then what is the sample mean? It's the x bar. And as you can see, x bar is really far away from the null. What does that mean? Does it mean x bar explains mu naught very well? Well, if they are very close, then yes, but they're really far away. So the answer is no. Consequently, in this case, we're going to reject H0 the null hypothesis and accept the alternative hypothesis in the end. But then again, here's a problem. How close is close enough and how far is too far? And that threshold is this x1 value over here, and that's given by the level of significance 0.05. What do I mean by that? This alpha is the area of this red region here, the wing part, or the probability that you end up with a sample mean less than x1 under the null hypothesis. Well, the probability blah 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 part may have been a little bit difficult for anyone to understand, except maybe for really top level students. So let's focus upon the graphical method. The area of this wing part corresponds to the level of significance alpha. This program is randomized, so we can run this program once again, and you're gonna get different x bar value. Ooh, too much difference. Still no good. Maybe I have to stop this and... Okay, I ran several more times until I get what I wanted. Okay, here we go. Let's look at the left-hand side picture. And this time, x bar is close enough to mu naught. X bar is where the end of this blue arrow is, and I just moved my mouse over there. And x bar is this time close enough to null. Null is mu naught. So we're gonna assume that x bar explains null pretty well. They match very well. Consequently, we're gonna accept h naught, h0, the null hypothesis, and we'll reject alternative hypothesis HA. But then again, the problem is how close is close enough? And that threshold is this x1, and that's given by the level of significance, the area of this red region. If I change this alpha value, then the game rule will change a little bit. For example, what if I change this into 2%? We're going to get smaller red area, as you can see over here, smaller red area. So it became a little bit more difficult to reject the alternative. It became a little bit more difficult to reject the null hypothesis because it's going to be a little bit more likely that x bar will come pretty close to mu naught. In this case, x bar is close enough to mu naught, close enough to null, so we're going to select null and reject alternative. This program is randomized, so we can run it again, and well, still here. Let's pause it and do it. Okay, I repeated running this program until I got into this red area. In this case, x bar is over here in the red region, and you can clearly see that x bar is really far away from the null. But then again, how far is far away? Well, that threshold is given by this x1 value, which we call the critical value, by the way, and that's given by the level of significance, alpha value. Now let's take a look at the right-hand side picture, and this is kind of similar to this time we're talking about, in this case, mu is greater than mu naught. And in this case, this x bar here, or at the end of this blue arrow here, where my mouse is, that's close enough to mu naught. Do you see that? Close enough to null. How close is close and how far is far? Well, here's a threshold, x2, which is given by the level of significance. This red area is 0.02 or 2%, and that gives you this critical value x2. That's the threshold. And x bar, the sample mean, is inside the threshold, which means it's close enough to null. So we're going to select null. Null is right. We're going to go with null. And okay, I learned my lesson. I'll pause the video and then run this program until I get into the red area. Okay, in this case, x bar is really far away from the null. But then again, how far is far and how close is close? That's answered by this threshold x2. And x2 is given by the level of significance. This red area where I'm moving my mouse around is alpha value. Because x bar is really far away from the null, so we're going to reject null and consequently accept alternative. What if I change this alpha value once more? Change to 0.1 and 10%. We're going to get this time much bigger red area here. Let's look at the left hand side picture. This area here, this wing part, is now 10%. And that's what this level of significance does. So if we have really big red area, which means it's more likely that we're going to go with alternative. Because if x bar falls into this red area, then we're going to accept alternative and reject null. But if we get something really, really small there, then it's going to be much more difficult to get alternative hypothesis. Really small area here, you see. Let's go back to the default 0.05. In some cases, we'll have to consider the two-tailed test, which is rather rare, but here's an example. In this case, we have to consider both wings because we are talking about just difference. So it can be too small or too big. So this red area and that area add up to the level of significance of 0.05. And in this case, x bar is too far away because it's beyond this threshold. So we reject null. In this case, x bar is close enough to null, so we're going to accept null. And that's how we work out this hypothesis testing. And exactly how do we do that? How do you calculate? Well, that's something we are going to consider in the next video. For now, we're talking about the structure, and the key thing is the role of alpha, the level of significance. And that was the area of the red region, the wing part, or that wing part, or some of these two wing parts, this and that one. In my opinion, that's the best way and the easiest ways to understand the level of significance alpha, but I'm afraid that's not the way our textbook author is doing. Our textbook explains kind of this way. Type 1 error is an error coming from rejecting the null hypothesis even though it is right. And type 2 error is an error coming from rejecting the alternative hypothesis even though it is right. And do they complement each other? No, not really. You see, alpha is the probability of type 1 error, which means the probability that we end up rejecting the null hypothesis even though null is right. Versus beta, which is the probability of type 2 error, where the probability of we're rejecting HA even though it is right. Because beta is very difficult to find out and in many cases pointless, we just try to minimize this one, alpha. So that's what the level of significance is all about. One more comment. This alpha and beta are, as a matter of fact, conditional probabilities because we have this if blah 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 part. This part is condition. Even though H0 null is right, and even though HA alternative is right. And please note that we are talking about two different conditions. For beta, we are talking about the condition where HA is right. For alpha, we are talking about condition where H0 is right. So we are talking about two different denominators, so they do not complement each other. You cannot calculate beta from alpha or vice versa. They're completely separate. We just look at alpha, and that's the level of significance.